In this demo, we'll take a look at how we can configure and interact with the table per type strategy. We're now back inside Visual Studio, and we're looking at the CardLog database context where we are configuring the item entity. With table per hierarchy, we didn't need to do anything explicit in order for IFCore to use it as our mapping strategy. With table per type, however, we need to specify for each entity that we want to map that it must have a table defined for it. If we like, we can do so by simply calling the toTable method on our entities like we see here and specify a name for that table, and do the same for each entity which exists in our type hierarchy. Doing so will allow us to specify names for each individual mapping table. Instead of doing this though, we could also take a shortcut and instead use the useTPT mapping strategy method on the item entity like we see here. This method was introduced with IFCore 7, and it tells IFCore that it must map all entities which inherit from the item entity using the table per type strategy, thus mapping each entity to its own table on the database. Before we create the migration, just note that the call to the isParse method has been removed here where we set up the production date columns for the dried food and canned food items. This is because that call is no longer relevant since we are now using the table per type strategy. Also note that the item type property has been removed from the item entity since we no longer have any concept of a discriminator column when we use table per type. As we shall soon see, a similar mechanic is actually in play when we execute queries under this strategy, but it is not implemented on our type as an explicit property or a shadow property. If we now create a migration based on this, we get a migration file that looks like the one that we see here. Notice that this migration was created in the context of having already applied the table per hierarchy strategy, so it would have looked different if we had used table per type right from the start. But doing things this way allows us to see the differences in terms of database schema between these two strategies. So what we see here is that first all the columns that do not specifically pertain to the item base class are dropped from the items table. And as we can see here, this of course also includes the item type column, which was used as discriminator column. The next thing that we can see here is that a table is created for the canned food item entity, which contains an ID column, a column for the canning material, one for the production date, and finally one for the expiry date. These columns we all recognize as properties of the canned food item entity. But the most interesting part is the bit of code that we see here where the primary key for the table is set up and a foreign key constraint is also added. If we take a look here, we can see that the ID property of the entity is used both as a primary key and also to create a foreign key relationship to the items table pointing to the ID column of that table. And as we can see here, the same thing goes on for the clothes item entity, where we first add the ID and fabric columns, and then set up the ID column to be both primary key and part of a foreign key relationship to the items table. And of course, the same thing happens for the dried food item entity and the magazine item entity. Now let's apply this migration to the database, and head over to the console application and try to interact with this new mapping. In order to do so, we'll run exactly the same code that we used when we demoed the table per hierarchy strategy. Before we get started, we should just be aware that all the items that were added during that demo have been deleted. So we'll once again add them, just to show that this happens in the exact same way as before. So let's run the code and see it in action. Like before, we'll quickly move past the first several lines of code here where we add the new entities to the database and clear the change tracker. After having done this, let's head over to the Server Explorer. As we can see, several entries have once again been added to the items table. And as before, we have the energy drink, the canned tomato soup, the dry tomato soup, the hiking shoes, the nodding rope, and the Climbers Quarterly. But here the similarities stop. We no longer have a discriminator, and we no longer have any columns mapped to properties that were specified on the canned food item entity or any other derived entity. If we want to take a look at, for example, the canned tomato soup and the energy drink, we can look in the canned food items table for entries with the IDs 1079 and 1080. Here we can see that the first entry, which corresponds to the energy drink, is made from tin, and that the second one, which corresponds to the canned soup, is made from steel. We can also see their production and expiry dates here, and if we open up the clothes items table, we can see that the hiking shoes are made from leather. If we now head back to the console application and move the debugger past this bit of code here, we fetch all items from the items table, and as we can see here in the watch view, we get 8 items back of the various types in our inheritance hierarchy, and we can once again see our canned food items, clothes items, and so on. But if we now take a look here in the output window, we can see that for this strategy, IFCore has executed a somewhat more complex statement on our database. So what happens here is that in order to fetch all types of entities, IFCore creates a select statement where it joins all tables involved in our inheritance hierarchy. Because we've set up the primary keys of all the tables that are mapped to entities that are derived from our items entity to also be foreign keys that point to the items table, and all IDs therefore originate in the items table, we know that there will be no duplicate IDs used across the derived tables. And because of this, we know that for any given entry in the items table, only one of these joins will be successful. This is used in the case statement that we see here, where we check whether data was returned from each of the joins, and based on this assign either magazine, dried food, clothes, or canned food item to be the discriminator column, which we return here. ifcore then uses this generated discriminator value to make sure that we only get the relevant entries back. If we now move the debugger one step further, past this bit of code here, we fetch all magazine items from the items table using the offType method. And as we can see here in the watch view, we get one magazine item back, which is the Climbers Quarterly. And if we now once again look in the output window, we can see that ifcore has executed a reduced version of the query that it used to fetch all items, this time only joining with the magazine items table. And if we take one more step with the debugger, past this bit of code here, where we use the magazine items collection to fetch the magazine items, we can see here in the output window that this executes a very similar query, only this time we do not create a discriminator, but instead we inner join directly between the items and the magazine items table. And if we look in the watch view, we can see that we once again fetched the Climbers Quarterly magazine, just like we would have expected. And in the same way, if we now proceed with the debugger, we fetch the canned food items. We can see that this executes a query that joins between the items and the canned food items tables. And if we move past the next bit of code here, which fetches dried food items, a query is executed that inner joins with the dried food items table. And if we move past the last bit of code here and fetches all the clothes items, a query that inner joins with the clothes items table is executed. In the demo that we just saw, we once again mapped our model to the database, this time using the table per type strategy. We did so by changing the mapping from table per hierarchy to instead using table per type. This was simply done by using the use TPT mapping strategy method on our item entity. Using this method is also how we would tell ifcore to use the table per type strategy if we were starting from scratch. But by making the transition from one strategy to the other, it became apparent how the switch meant that we had to remove all the columns related to the derived types from the items table and instead create specific tables for these entities containing columns for the properties specific to these types. We also looked at the SQL statements that ifcore generated for us when we used this strategy, and we could clearly see that it made extensive use of joins, which is the main reason why this strategy is no longer recommended. The last strategy that we'll look at is table per concrete type, which was introduced in ifcore version 7. In the table per concrete type mapping strategy, all the types in our inheritance hierarchy are mapped to individual tables, just like we saw with table per type. But table per concrete type does not have any foreign key relationships between the base table and the derived tables. And if the base type is abstract, it is simply not mapped to any table at all. When we use this strategy, only concrete types are mapped, hence the name. Instead of a normalized schema like we had with table per type, table per concrete type gives us a denormalized schema where each of the tables that map to types in our hierarchy contains columns for all properties on the entity type to which they are mapped. This helps address some of the common performance issues we get when using the table per type strategy. This is because with the table per concrete type strategy, table joining will not be required. Instead of having to join between base and derived entity tables, table per concrete type uses union all when creating SQL queries that fetch data from several entity types at once. This is possible due to the denormalized nature of the schema created for table per concrete type and gives us faster query execution since utilizing union all has better performance than table joining does. And this difference becomes even more pronounced when we are querying for leaf type entities. A leaf type is a type in our inheritance hierarchy that is at the end of any of the branches of that hierarchy. In other words, it is a derived class from which no other classes derive, such as our dried food and canned food item entities. The reason why table per concrete type performs so well is that, as mentioned, using this strategy will result in a denormalized schema for our entities. This means that each mapping table will contain columns for all the properties of the entity that it is mapped to, regardless of whether a property is defined on the specific entity or derived from a base class. This is quite different from the schema that we get when we use table per type, where data is highly normalized, which leads to the need for table joining. This denormalization has some consequences for how primary keys are defined when we use this strategy. ifcore requires that all entities in a type hierarchy have unique key values. This is easy with table per hierarchy where there's only one table whose entries will naturally have unique keys. With table per type, uniqueness is guaranteed by the fact that any tables containing derived entities have a primary key, which is also a foreign key that points to the primary key in the table containing the base class. This means that for each entry in a table that contains derived entities, we always have an entry in the table that contains the base entity, and these two entries are connected by the relationship between the primary keys. This means that for table per hierarchy and the table per type mapping strategies, simple identity columns can be used for ID generation. This was also the case for the tables that we generated when we used these two strategies in our demos. But things are not quite so simple with the table per concrete type strategy. This is because all the entity types in our hierarchy will be distributed across unrelated tables, and there is no central table used for containing IDs. This means that using primary keys based on identity columns for our mapping tables is not possible when we're using this strategy. If we tried using identity columns, we would end up having unique keys in each individual mapping table, but we would have no way of ensuring uniqueness across all the tables. So another solution is required to ensure unique keys for this strategy. The specific solution that we end up with will depend a lot on the database on which our model will be deployed. In our case, where we used the SQL Server database, unique keys are generated by drawing them from a sequence that is used across all tables involved in the hierarchy. Since such a fully denormalized schema will distribute the primary keys for our derived types across their various mapping tables and will not contain a central table keeping track of these IDs, we cannot create foreign keys that point to the base entity in our hierarchy, but only to derived classes. So if we want to include an instance of our base class in another class, the relationship cannot be set up as a foreign key relationship on the database. As we shall soon see in the demo when we do so, ifcore creates a column that is used to contain keys for the base class, but it is not backed by a proper foreign key constraint. This does not have to be a problem though, we just need to make sure that our applications do not attempt to insert invalid keys in our tables. If we use ifcore for inserting all data and use relevant navigation properties when fetching the related entities, it will work in practice like a regular foreign key relationship. This is because ifcore will make sure that all columns referencing the base entity will always contain valid primary key values, and will create the relevant joins for us when we use the navigation properties. And once again, let's take a look at our item model, this time in the context of the table per concrete type strategy, and let's see how we can map it to the database using this strategy. Just like the table per type strategy, table per concrete type creates a table for each of the individual types in our inheritance hierarchy. But this time each of these tables are fully described, containing all the data related to its entries. So once again we have the items table, but this time it only contains a single item, the nodding rope, since this is the only item which is directly derived from the item entity type. Other than that, the table looks exactly like it did before when we used the table per type strategy, and it contains the ID, the description, unit price and unit weight of each entry. And if, for example, we now look at the canned tomato soup entry in the canned food items table, we can see that this table now also contains columns for all properties related to that entry, such as date of expiry and production date, but also the description and unit price properties. And of course the same goes for all other types of items such as the hiking shoes and the dried tomato soup. As we discussed, this is an example of a denormalized schema which has a lot of redundancy between the tables. But as we shall see during the demo, this setup has a lot of advantages because we avoid all the joins that were involved in using the table per type strategy. So if, for example, we would like to fetch the hiking shoes here with ID 1028, ifcore will simply create a query directly on the clothes items table fetching the entry with ID 1028. This will perform much better than the query that we would have to make with table per type, since that would involve joining with the items table.